Hello dear students. So now we will continue discussions on the gas constant, the universal gas constant and other aspects of thermodynamics. So we have seen in the last class that we define what is called as the specific gas constant of a particular type of gas, of a certain type of gas for 1 kg of mass, let us say. So this constant is called as the gas constant, or this is also called as the specific gas constant. So this is specific gas constant for a given type of gas for 1 kg of mass, right. Then we defined the number of moles, and we realized the number of molecules in a kilomole of any material is a constant known as the Avogadro's constant or Avogadro's number. So any gas of 1 kilomole, that means any gas weight divided by the molecular weight will have the same number of molecules. And the Avogadro's hypothesis says that gases containing the same number of molecules occupy the same volume at the same temperature and pressure, right. So this is the most important thing. So you keep the temperature and pressure constant, will occupy the same volume, right. Now you define another gas constant, or so that means that a kilomole of any gas, the value of gas constant will be the same. So here what you are doing is you have defined R star is called as the universal gas constant. Universal gas constant is 8314.2 joule per degree per kilomole. So we know that for a specific gas, the gas constant can be defined again from R star is equals to m times R, right. So R is your specific gas constant, right. So basically the idea was you have defined R for 1 kg of a gas, a particular type of gas, and you have defined R star, which is the same for any 1 kilomole of any gas. So you take the molecular weight, then you can get back the R star as R times capital M. So we can thus write, you can use this equation into the earlier gas equation, which was P alpha is equals to RT. You can use in terms, instead of R, you can use R star by M times T. So which you can write as, so the number of moles PV is equals to N R star T. So the gas constant for one molecule of gas. Now gas constant for 1 kilomole of any gas is the universal gas constant. Gas constant for 1 kg of a specific gas is the specific gas constant. Now gas constant for 1 molecule of any gas. So you take the universal gas constant, you divide the Avogadro's number of 1 kilomole, the number of molecules of 1 kilomole, because this R star is eventually, R star is 1 kilomole of a gas. So you divide by the number of molecules that this 1 kilomole will have, which is a constant again. So the universal gas constant divided by the number of molecules in 1 kilomole is again a constant, which is called as the Boltzmann's constant. So we make use of all these constants at several instances, right. Let us say for example dry air. So what is dry air? Dry air is the mixture of gases that we see in our atmosphere. Generally we don't talk about moisture, then we are talking about dry air. So for any gas containing molecules per unit volume, n number of molecules per unit volume. So n is eventually a number of molecules per unit volume. So it has the dimensions of 1 by volume, right. It does not have any dimensions of the mass, right. It has the dimensions of 1 by volume, or mass by volume is the density, right. So you can get rid of the density and replace it with number of molecules per unit volume. We can write the equation of state as P is equals to NKT, right. So this volume term is now in this and the Boltzmann's constant has the information of R star by Na into N into T, right. So we consider dry air to be the mixture of gases in atmosphere, including water vapor. Okay. So dry air is the air that we see around ourselves, right. Now let us say if the pressure and specific volume of dry air are So, pressure is PD and the specific volume occupied by 1 kg of air is alpha d. Then we write the equation of state as PD alpha d is equals to RdT. See here, the suffix d indicates it is for dry air, so it is not for a single species gas, it is for a mixture of gases. Generally, we know the mixture of gases is oxygen, nitrogen, carbon dioxide, argon, right. So, this is the combination that we know very well in the lower altitudes, in up to let us say 10 kilometers or 5 kilometers, right. So, this mixture of gases is referred including water vapor, this mixture of gases is called as the dry air, fine. So, if you take dry air, if you know what is the pressure that the dry air exerts, PD, what is the volume that 1 kg of dry air will occupy, alpha d. If you know what temperature is at which you have made the measurements, that is capital T, you can write the gas equation as PD alpha d is equals to RdT, where Rd is the specific gas constant for 1 kg of dry air, right, 1 kg of dry air, right. Now, you can form 1 kg of dry air out of different proportions of O2, N2, CO2, argon and CO2, H2O, right. But in the atmosphere, we know what proportions are these gases existing, right. So, we can calculate 1 kg of dry air can be made up out of these gases at a particular proportions, right. So, now here we define what is called as the apparent molecular weight. Previously, the molecular weight, the idea of molecular weight was with the assumption that whenever you talk about a gas system, it is a single species gas, but here we have a mixture of gases. So, we can now define the apparent molecular weight of dry air as the total mass of constituent gases in dry air divided by the total number of moles of constituent gases. Understand? So, in the number of moles, the idea of number of moles is the weight, let us say, divided by molecular weight. So, generally we write it as small m, weight divided by molecular weight. So, here we define the apparent molecular weight of a mixture of gases as the total mass of constituent gases in dry air divided by the total number of moles of constituent gases, because unequal number of moles will be present in the total 1 kg of air that you take, right. So, simply with this idea, so here n is what, m by capital M, right. So, now here capital M, the apparent molecular weight. So, this is if it is a single species gas, you will simply write capital M. If it is a multi-species gas or if it is a mixture of gases, the apparent molecular weight, let us say we call it as Md, is nothing but m by n. Now, n is the number of moles. So, the total number of moles are to be calculated out of number of moles of each gas. So, sum over mi, what it means is sum over the mass of individual gases, oxygen, nitrogen, so on, divided. So, it has to be sum of n. Sum of n is now, number of moles is again weight by molecular weight, right. So, mass of ith species divided by the molecular weight of ith species, right. So, here you make this, you substitute this into this. So, eventually you are getting this. So, mean molecular weight or the apparent molecular weight of dry air is defined as the total mass of the constituent gases. You take any volume, you take this, then you divide by the total number of moles of constituent gases. So, how many moles of carbon dioxide are there? So, for example, if I want to write for a combination of CO2, N2O and let us say H2O, what I will write is, so the mean molecular weight of dry air is sum of mass of CO2 plus mass of N2 plus mass of O plus mass of H2O divided by, let us say, number of moles of CO2 plus number of moles of O2 plus number of moles of N2 plus number of moles of H2O. So, this is the idea, right. So, why do you need MD? see you have defined R star as capital M R, right. That means if you want to calculate the specific gas constant of dry air at various concentrations, if you keep changing the concentrations, every time you change the concentration, the value of the specific gas constant will change, right, will change. But if you want to calculate, every time you want to calculate the specific gas constant for different combinations of these concentrations, what you can do is you can calculate the mean molecular weight, and then if you know the universal gas constant, you can do that, right. So, simply speaking, so where small m and capital M represent the mass and the molecular weight of the ith constituent, it can be made up of any number of constituent gases. You can always say that small m and capital M represent the mass and molecular weight of the ith constituent, right. So, consider a mixture of two gases occupying volume V consisting of N1 number of molecules of gas 1 and N2 number of molecules of gas 2. So, for example, you consider a mixture of gases in a volume. So, the volume is fixed. So, gas number 1, let us say oxygen, and gas number 2 as let us say nitrogen, both of them are in this enclosure. Interestingly, gas number 1 has N1 number of molecules and gas number 2 has N2 number of molecules, fine. But here we are talking about the mixture. So, the total pressure exerted by the mixture of this gas on the walls will be the total pressure, that is the total momentum transfer that is happening by both the molecules. So, how do you define? I mean, the pressure is the momentum transfer, right, built up by the momentum transfer. So, the total pressure is a sum of pressure exerted by the oxygen atoms and pressure exerted by the nitrogen molecules, right, both of them. So, ideal gas equation can now be written as P is equals to NKT, right. So, the total number of atoms or molecules per unit volume, total number is N1 plus N2. Now, if you split this, you will realize that the pressure, the total pressure that is exerted by the mixture of gases is the sum of individual pressures. So, this you can call as P1 and this you can call as P2. P1 is due to gas number 1 and P2 is due to gas number 2, as simple, right. But, so the first term, yeah, so it is the same thing that I am speaking of. So, the first term on the right hand side is exactly the pressure exerted by the gas 1 if it is occupying the entire volume by itself, right. And P2, so here V is appearing in the denominator, right. So, if you take this equation alone, it appears gas with number of molecules of N1 at a temperature T occupying a volume V will exert a pressure. Similarly, you can also say this is P, right. So, the total pressure is the sum of individual pressures as if the one species of gas alone is occupying the entire volume by itself, right. So, that is the idea. So, this pressure is called as the partial pressure of the gas. So, always remember partial pressure is never equal to the total pressure of the gas. Partial pressure is the pressure exerted by one constituent of a mixture as if it is alone occupying the entire volume by itself, right. So, this same is valid for the second term as well, right, like I said here, right. So, we can say that the total pressure is sum of the two partial pressures, right. The most important thing of all this discussion is that we always assume that these gases are not interacting among themselves. So, there is no chemical interaction that is happening within the mixture of gases. If it happens, then it's a different story. So, this idea is expressed by the Dalton's law of partial pressures, which states for a mixture of k component gases, each of which obeys the ideal gas law, the total pressure P exerted by the mixture is equal to the sum of partial pressures which would be exerted by each gas if it alone occupied the entire volume at the temperature of the mixture of the gas, right. So, this point is enough emphasized already, but this temperature is the mixture temperature. So, if it is at the same temperature, but if it is occupying the same volume, but in reality it is not the only gas which is occupying the same volume, it is a mixture of gases which is occupying the same volume. So, in that case the pressure will be the sum of partial pressures. So, that is the idea. So, we can write that, so the total pressure is the sum of partial pressures, and I goes from I to K, where I also said that it is a K component gas. I mean, there are K different components inside the gas which are exerting this pressure, right. So, if the volume of the mixture is V and the total molecular weight of the ith component are total mass and the molecular weight of the ith component are Mi and capital Mi. Mi is the mass, how much amount of gas is present, and what is the molecular weight of that species of gas. So, if the volume of the mixture is V and the mass and molecular weight of the ith constituent are Mi and capital Mi respectively, then for each constituent we can write the equation, where we are not changing V, we are not saying that this gas will occupy only a certain volume, no, it is occupying the entire volume, and this capital T is the temperature of the mixture, you always remember this. So, this is the temperature of the mixture, right. So, when we apply the Dalton's law, we can write the pressure of the mixture as, so this is the sum of all the different partial pressures. So, each I will be one partial pressure, right. So, here R star is a constant which is now universal gas constant. Now, since you are accompanying with the molecular weight, you use R star. Temperature is a constant, I mean, it is the same for all the gases, so you pull it out. So, the pressure is now written as R star T divided by V sum over I to K Mi divided by Mi. So, this is what? So, this is eventually Ni, right. So, the total mass of the mixture is a sum of individual masses of the constituents, we know that. So, we can write the total pressure of the mixture of gases as total pressure. So, M is the sum, right. So, we have written P is equals to R star T divided by V sum over I to K, this is N divided by M. So, right, N is equals to M by capital M, right. So, so R star, if you take it, so this is this alpha, this is the specific volume alpha. So, P is equals to P, the pressure can be written as in terms of the gas constant, right. So, what I have done is I have used the form of the mean molecular weight of a mixture of gases, right. So, for this equation has to hold dimensionally, we will require this to be equivalent to the mean molecular weight. So, for this equation to obey the ideal gas law, it must satisfy the following. So, P is equals to RT by alpha. So, this is the original form, P alpha is equals to RT, right. So, then you require that this R star, so R is the specific gas constant. If you put R star, then the mean molecular weight should come here. So, such that the mean molecular weight M bar is the mean molecular weight of the mixture. So, we can write M bar as M mass of the individual gas constituent, total gas, divided by the total number of moles, right. So, this is we have already defined. I mean, so let us say for example, so the basic idea is this, the basic idea is the mean molecular weight of a mixture of gases having I different component gases is the sum of mass of individual gases divided by the sum of the number of moles of individual gases, right. So, we take an example for our planet, let us say the lowest 25 kilometers of the atmosphere is made up of almost entirely by nitrogen, oxygen, argon and carbon dioxide, right. So, N2, O2, argon and carbon dioxide make up nearly 100% of the atmosphere, right. So, their percentage of occurrence is 75.51, 23.14, argon is 1.3, carbon dioxide is 0.05 by mass, not by volume, not by number, by mass. So, of the entire mass of atmosphere, 75.5% is nitrogen, 23.14% is oxygen, 1.3% is argon and 0.05% is CO2, right. So, now we know the molecular weights of these species, right, we know, let us say, we can calculate what will be the mean molecular weight of the gas, of the dry air, right. How can we calculate the mean molecular weight of the air? So, let us say, so according to the formula, mean molecular weight is, let us say, is defined as the total mass, right, and the total number of moles. Weight by molecular weight is number of moles. You take in grams, let us say. This is for argon, for CO2 and etc. right. So, you take one, let us say, you take 100 grams of dry air, okay, 100 grams of dry air. So, since it is by mass, so we can say that 75.51 grams will be nitrogen, 23.16 will be oxygen, 1.3 will be argon and 0.05 will be carbon dioxide. So, you just substitute these things. So, in the numerator you are accounting for the total mass, and in the denominator you are accounting for the total number of moles. That means, each gas has its own weight by saying that its weight is different and its number of moles are also different. A heavier gas will not have enough number of moles to be able to influence the molecular weight in a certain way. So, if you calculate the mean molecular weight, it will be 28.97 gram per mole, in gram per mole. So, per 1 mole, the mean molecular weight, it will be 28.97, right. Or if you say it in kgs, let us say 0.02897 kg per mole. So, now if you know the mean molecular weight, you can simply calculate the specific gas constant of dry air. So, if you want to use P alpha is equals to RT, but not R star T. That means, your gas constant is specific for this combination, for these percentages. If you want to use a gas constant which is R at a given value of temperature, you can use this value 287 joule per kg per Kelvin. So, this is the specific gas constant of dry air. This is again as per 1 kg of, for 1 kg of dry air, right. So, there is something about the concept of mean molecular weight, how the mean molecular weight is useful to understand certain aspects about the mixture of gases and things like that, right. So, from the next class, we will try to include certain humidity variables into the discussion, let us say, by bringing water vapor, H2O, right. So, we can stop here. We will continue the discussions on atmospheric thermodynamics in the subsequent classes. Okay.